Welcome back. We know you want to get smart on important topics fast. Today, we're tackling something pretty fascinating in advanced AI. It's this challenge. We have these large reasoning models, LLMs, getting incredibly good at complex math, seriously tough problems. But how do we make sure they also reliably follow instructions? It's not always straightforward.
It really isn't. There's this tension that researchers are uncovering. A model might be brilliant at reasoning, but, well, surprisingly bad at just doing what you ask it to do. And that's exactly what the paper Scaling Reasoning, Losing Control digs into. It explores this relationship head on.
Right. And they didn't just rely on existing methods, did they? They developed something new for this.
They did. They created MathIF, which is basically the first benchmark designed specifically to test instruction following in these math-focused reasoning models.
Why was that needed? Weren't the general tests good enough?
Well, the existing benchmarks like ifeval or followbench are often more general. They're not really tailored to the nuances of, mathematical problem solving combined with instruction following.
Okay, so MathIF is different. How so? What makes it specific to math models?
It uses 15 different types of instructions or constraints, and crucially, these can all be checked automatically by a program, so no subjective judging needed. They fall into four main categories. Things like the length of the answer, specific words that must or must not be used, formatting rules like punctuation, and requirements about prefixes or suffixes.
15 rules, and I gather they don't just test them one at a time.
No, that'd be too simple, probably. They programmatically combine these constraints, so a prompt might have two rules or even three that the model has to follow simultaneously.
Ah, okay, making it more complex.
Yeah, mirroring real-world scenarios a bit more. And they apply these multi-constraint prompts to math problems across a range of difficulties. This gives them, in the end, 420 distinct test cases.
Sounds pretty comprehensive. So the big question, how did the models actually do on MathIF?
The results were quite revealing. They tested 23 different large reasoning models.
Yeah.
And the overall picture, most of them really struggled to follow the instructions consistently.
Really? Even the big, powerful ones?
That's the surprising part. You might intuitively think, a larger model, a more capable model, would be better at following instructions. But the data didn't consistently show that. Size didn't guarantee better control.
That's counterintuitive. I mean, more reasoning power should mean better understanding of what's asked, shouldn't it?
You'd think so. But even the top performer in their tests, Quen 314b, only managed about 50% accuracy on strict instruction following, meaning getting all the combined rules right. And performance tended to drop when the math problems got harder or when more constraints were layered on.
So it's more complicated than just raw mathematical ability. What do the researchers think is causing this disconnect?
They talk about a mutual interference. It seems the processes for reasoning and for following instructions can actually clash with each other. Think about how these models are trained. Techniques like supervised fine-tuning or SFT, where you show it lots of correct reasoning examples, or reinforcement learning, RL, where you reward it for good reasoning steps.
Right, training them to be better problem solvers.
Those methods are effective at boosting reasoning skills, no doubt. But the paper found they often make the models worse at sticking to instructions. It's like improving one skill actively degrades the other.
Wow, okay. So the very act of making them smarter at math could be making them less obedient, for lack of a better word.
That seems to be the core finding, yes, this losing control aspect. And this issue seems to get worse when the models produce longer chains of thought.
Chain of thought. That's the step-by-step reasoning they show, right?
That's right. The model sort of thinks out loud. And the longer that process gets, the harder it seems for the model to maintain focus on the original instructions.
Okay, so what happens if you force them to be brief? If you limit that chain of thought, does that help with instructions?
It can, yes. Enforcing brevity, telling the model to keep its reasoning short, tends to improve instruction following.
But there's a catch, I assume.
There is. That often comes at the expense of the reasoning quality itself. The model might follow the rules better, but the math answer might be less accurate or the reasoning less deep.
So it really is a trade-off. Better reasoning, worse instructions. Better instructions, maybe worse reasoning. What else stood out from the experiments? Any specific model types?
Well, like I said, overall performance on instruction following wasn't great across the board, but the Quen 3 series of models was a consistent bright spot. They performed relatively well on instructions across different model sizes in that family.
Interesting. So it's not just about size, maybe something about the Quen 3 architecture or training.
Possibly. It suggests design choices matter a lot beyond just scaling up. The research also hinted that maybe explicitly separating the reasoning steps, perhaps using special tags like think, could help. Models that just blend reasoning and the final answer seem to have more trouble with instructions.
And did adding these instructions impact how well the models actually solved the math problems correctly?
For most models, yes, it did. Adding constraints often led to a drop in their mathematical accuracy. It suggests that the effort of trying to follow the rules interfered with their core reasoning ability.
So they get worse at math when you tell them how to answer.
For many, yes, though there were a couple of interesting exceptions. Models like Quen 2.5, Math 1.5b, Instruct, and OpenReasoner 032b seem to handle the instructions without sacrificing, or in some cases even slightly improving, their math correctness. But they were outliers.
Let's go a bit deeper then. Did the type of math problem matter? Or the number of rules?
Definitely. They saw that models generally did better at following instructions on easier math problems, like those from the GSM-8K dataset compared to, say, Olympiad problems. And as for the number of constraints, when you looked at hard accuracy, getting all rules right, performance generally went down as you added more rules. 2 rules were harder than 1, 3 were harder than 2. Makes sense.
Okay, that's logical.
But interestingly, when they looked at soft accuracy, just counting how many individual rules were followed, even if not all were that sometimes stayed stable or even slightly improved with more constraints.
Huh. So maybe they try to follow more rules, even if they fail to get the whole combination right.
That could be one interpretation. It shows the complexity of juggling multiple demands. They also broke down the errors. You could have correct math followed instructions, correct math unfollowed, incorrect math followed, and incorrect math unfollowed. And the striking thing was how few cases fell into that first category, correct, followed. Getting both the math right and following all the rules perfectly was rare for most models.
That really underscores the trade-off, doesn't it? It's hard to do both well simultaneously.
It seems so. And they found that the drop in math correctness caused by adding instructions wasn't necessarily tied to how hard the original math problem was. It could happen on easier problems, too.
And you mentioned the chain of thought length before. How strong was that link?
Pretty consistent. Longer chains of thought generally correlated with worse instruction following. It's like the model loses track of the initial constraints as it gets deeper into the reasoning steps.
We touch on training methods like SFT and RL. Did the study look more closely at how these impact instructions following?
Yes, they compared different strategies. Models trained only with SFT, models with SFT plus RL, and models trained with RL right from the start. And the consistent finding was that while SFT and RL definitely helped the models get better at reasoning, they didn't really improve instruction following. In fact, they often made it slightly worse.
Even if you specifically rewarded following the rules, like formatting rules.
Even then, they tried using rewards that were aware of the required format, but it had a very limited impact on improving overall instruction adherence.
So the standard ways we make these models better reasoners might be inherently pushing them towards ignoring instructions. That feels like a significant issue.
It points to a fundamental challenge in current training paradigms. They did more experiments focusing just on coast length, too. For instance, they artificially forced models to produce longer chains of thought. When they did that, instruction following accuracy dropped.
Makes sense, given the correlation.
And when they controlled the maximum length of the response during RL training, allowing longer responses improved reasoning scores, but again, instruction following suffered. Shorter allowed responses did the opposite.
But wasn't there a simple intervention they tried? Something about repeating the instruction?
Ah, yes. They tried a very basic fix. Just appending the original constraint again at the very end of the model's generated chain of thought, right before the final answer.
Did that work?
It actually did improve instruction following noticeably, which is interesting, right? Such a simple reminder helped.
But I bet there was a cost.
A slight one. It came with a modest decrease in the mathematical reasoning accuracy, so even that simple fix highlights the underlying tension.
Okay, so pulling this all together, what's the main takeaway for us trying to understand these incredibly smart AI models?
I think the core message is this. There's a real significant trade-off happening between the reasoning capability of these large models and their ability to reliably follow instructions. And it's something that's maybe been overlooked.
And simply making them bigger or better at reasoning doesn't solve the instruction following problem.
Not automatically, no. The scaling helps reasoning, but it doesn't seem to inherently improve controllability and might even hinder it depending on how it's done.
And current training methods might even be making this tension worse.
That's what the evidence suggests. Methods like SFT and RL while great for reasoning, don't seem to help and might slightly hurt instruction adherence. It implies we need new approaches.
So future research really needs to figure out how to train models that are both powerful reasoners and reliably controllable.
That seems to be the challenge laid out by this work. How do we build AI that is not just intelligent, but also aligned with our intentions and directives?
It leaves you wondering, doesn't it? As these models get even more capable at reasoning, how do we ensure they remain tools that reliably do what we need them to do? Something to think about.